Hello, Comets. Today we're going to be discussing how to rank amines by their basicity. So I have this example here, and we're going to rank these where 1 is the most basic and 4 is the least basic. Now there's a lot of information here in this that you have to be able to put together, so I'm going to try and break it down and make this as simple as possible. So I'm going to start out by briefly defining what a base is again. So in the Bronsted definition, you have a base is something that is accepting an acidic proton. So let's just draw a quick example here. And we could have a hydronium ion floating around. Well, this nitrogen's lone pair is going to act as a base and take this hydrogen from this water molecule to make our conjugate acid. So the nitrogen in this case was acting as the base and it accepted an acidic proton. So for that to happen, we needed the lone pair. So we're going to keep that in mind as we go through this example here. So let's start looking at these examples here. Well, right away, I need to know this is aromatic currently, right? We have 2, 4, 6 electrons that are sp2 hybridized. This is sp2, right? It can resonate, and thus it will be sp2. They are conjugated and planar. So right here, I have an aromatic molecule. So if I protonate this and form its conjugate base, let's draw that real quick. I just made an aromatic molecule into a non-aromatic molecule. And as we've been saying for a long time, aromatic molecules are very stable, and this is not going to want to happen. So right off the bat here, this will be the worst base, because you do not want to break the aromaticity of a molecule. Now, just as a quick review, in case you don't remember, an aromatic molecule must be planar, sp2 hybridized, conjugated, and have 4n plus 2 electrons in the ring, where n is any number 1, 2, 3, 4, 0. So that's just a quick review. So now let's go to these other 3 examples here. So when ranking amines, one of the main things we rank by is the type of orbital. So let's look at these molecules here and find their hybridization. So what is the hybridization on this guy? Well, this one is sp3. And I'll draw it a little bit differently to help you guys see that in case you've forgotten how to do hybridization. We can do this. And we're going to count everything, including lone pairs once. So the bonds and lone pairs, you count them. So you say S, P, P, P. So it's sp3. I'll redraw this one to make it a little clearer as well. Now this one's a little bit tricky, and you have to remember some of your OChem 1 rules. That if it can resonate, you always take the lowest hybridization you can. So since this can become sp2, right, because it can resonate, etc., this is going to be sp2. And that's because if we were to draw what this looks like, it would be NH, H, plus here with the ring down here. So that's why that one's going to be sp2. So we've labeled that one as sp2. Let's clean this up a bit. Now this one, what is this one? Well, this one we can see is already sp2. So it's spp, so this one is sp2. Now the question is, which one's more basic? Well, we need to think a little bit about this. So if something is sp2, so I'll draw that here, it means we took one s orbital, which looks like a sphere, and 2 p orbitals, which look like these weird dumbbell things, and hybridized them together. Well, p orbitals are longer than s orbitals, so that's going to stretch the bond out. Now, if I took the sp3 example, we have sp3. Well, we took 1 s orbital and 3 p orbitals. Now, the p orbitals are longer, and they have, this one has 75% p character and only 25% s character, where this one has around 33% s character and 66-ish % p character. So this one is a smaller bond. It's shorter. Double bonds and sp2 bonds are shorter. So our nitrogen nucleus is closer to the hydrogen atom, if this was protonated, than this one, which would be further away. So there's an electron in this bond, and these electrons, since they're further away, aren't feeling as much of that effective nuclear charge coming from the nitrogen's positively charged nucleus. So this electron is not pulled away from this hydrogen as much. So since the hydrogen has its electron more, it is less acidic, because remember, taking electrons away from the proton makes them a positively charged proton, and that's the definition of an acidic hydrogen. Whereas in our sp2 example here, the nitrogen is closer to the hydrogen, and thus its electron feels more of the pull from the positively charged nucleus, which is going to make it more positively charged over here from its electron being pulled away from it more often, and that's going to make sp2 more acidic than sp3. So you can think of basicity as the opposite of acidity. So sp3 is more basic than sp2 is more basic than sp. And if you remember this example and kind of understand what's going on, it's hard to get them confused because you won't be like, oh, I can't remember, is sp more acidic than sp3? How does it go? So let's erase this. And right there, we can compare two of our molecules just off that information. So we have, this one is sp2, this one is sp3, and this one is sp2. So we know right there that this is the most basic molecule. Now the question is this sp2 atom or this sp2 atom more acidic? Well, let's look at where the electrons are. So these electrons, we said it's sp2, right? Which means we used one s orbital and two p orbitals, leaving us with one p orbital available for this molecule. And it's occupied by this bond right here, right? This bond is taking up the p orbital. Because remember, resonance occurs through p orbitals. So this electron pair is in an sp2 orbital. Whereas this one, it is sp2 hybridized as we showed earlier, but this can resonate. And to resonate, remember, it has to be in a p orbital. So this lone pair is in a p orbital. So you can remember p orbitals are more acidic, or you can kind of think about it. If you think about this sp2 lone pair cannot resonate. And that means it is always there. So if I redraw this molecule, it's never resonating. These are resonating, but this lone pair here is in the sp2 orbital, and it's always there. Which means when an acidic proton comes by, it is able to always attack to form the conjugate base. Whereas in this one, some of the time, this molecule, is big. Some of the time, these lone pair are in the ring here, and I'll leave it like this. I won't draw the resonance structures. And when that occurs, the lone pair is no longer here, right? We got that resonance structure we showed earlier. Where we push the electrons onto this minus, plus, and we also now have a positive formal charge on the nitrogen. So this resonance structure occurs just on its own, and if these electrons are in the ring, they are not available on the nitrogen to attack a proton. And now you could ask, why is this lone pair here? It's on a carbon. Isn't it going to attack a hydrogen? Well, the answer is no, because that would break the aromaticity of this ring. So that is not going to happen in this case. So I hope that helped, and let's rank these then. So we're saying that this one is more basic than this one, for that reason right there. So if you guys have any other questions, you can always stop by the tutoring lab to ask one of the tutors, and we'll gladly help you out. But for now, I hope that helped, and I wish you best of luck on the rest of your semester.